What I'd like to do is show you how de Moivre's theorem for powers is derived. So we know that if we have, let's say that Z is R cosine theta plus I sine theta, and I want to use the notation cis, and CIS stands for cosine theta plus I sine theta, where this is the angle. So cis allows us to write this long statement more simply. And if I have Z times Z, we said that products are found by multiplying the modulus and adding the argument. So this should be R times R cis theta plus theta. And we can kind of make this look nicer. Z times Z is Z squared. R times R is R squared. And theta plus theta is 2 theta. And we can do this again. Z squared times Z is R squared times R. This of 2 theta plus theta, because the modulus of Z is R, the argument of Z is theta, the modulus of Z squared is R squared, and the argument for Z squared is 2 theta. And if we add and multiply, we get that Z cubed is R cubed, fifth of 3 theta. And this isn't really a proof, but you can see that this process can be generalized. So that Z to the N is equal to R to the N, cis N times theta. This is de Moivre's theorem for powers, where N is an integer. Find Z cubed and Z to the fifth if Z is 1/3 cosine 3 pi over 4 plus I sine 3 pi over 4. So let's see. For Z, R is equal to 1/3, and theta is equal to 3 pi over 4. When N is equal to 3, we have Z cubed is equal to 1/3 cubed cosine, and let's see, N, so 3 times 3 pi over 4 plus I sine 3 times 3 pi over 4. Well, I know what 1/3 cubed is, because 1 cubed is 1, 3 cubed is 27. So we have a modulus of 1 over 27. 3 times 3 pi over 4 is going to be 9 pi over 4. So that's pretty easy. That's z to the third. Let's find z to the fifth. So this time we have 1/3 to the fifth power. Fifth 5 times 3 pi over 4. Well, 5 times 3 is 15. So we're going to have, and 3 to the fifth, 27 times 9. 18 plus 6. 243, is that right? So we have 1 over 243, fifth of 15 pi over 4. So what if our original complex number is given in rectangular form rather than polar? Because de Moivre's theorem is based on a polar representation of the complex number. So when we start with a number that is given in rectangular form, we want first to change this into polar form, and then we can easily find the power. And what we're going to do is find it using de Moivre's theorem, and then find it also by multiplying complex, just in rectangular form, and see which one is easier. So I know that here z is equal to a plus bi, so that a is -1 and b is square root of 3. We know that r is the square root of a squared plus b squared. A is -1. B is the square root of 3. -1 squared is 1. Square root of 3 squared is 3. 1 and 3 are 4. And the square root of 4 is 2. Now that's sweet. Also, we know that the tangent of theta is going to be b over a. Oh, let's take a notice that z, -1, 3. So z is in quadrant 2. When we take the inverse tangent, we're going to have a negative number, but that inverse tangent will always be given in quadrant 4, because the inverse tangent is defined in 1 and 4. And then we have to move that angle into quadrant 2. So I want to go ahead and take the arctan of both sides. So that we have arctan. Let's see, b is square root of 3. A is -1, so just negative square root of 3. Well, what angle has sine with a square root of 3? because remember, tangent is sine over cosine. So that square root of 3 is in the numerator. It must be pi over 3, so negative pi over 3. This angle lives in quadrant 4. To move the angle into quadrant 2, we're going to take pi and subtract pi over 3, and we get 2 pi over 3. So our angle is pi minus the angle we found, and we know we need to do that because we can see that z is in quadrant 2. So now I know that we can write z as 2 cis 2 pi over 3. I wanted to find z to the 4th. Got 2 to the 4th cis 4 times 2 pi over 3. 16 cis 8 pi over 3. And now we do want to go back to rectangular because we started with rectangular. So anytime you start with rectangular, you want to end with rectangular. And let's see, 8 pi over 3, that's bigger than 2 pi. So let's see, 8 pi over 3 minus 2 pi. So let's see, 8 pi over 3 minus 6 pi over 3 is 2 pi over 3. That's interesting. So we've got 16 times the cosine plus I sine of 2 pi over 3. Let's see, cosine 2 pi over 3 plus I sine 2 pi over 3. Again, I know I'm in quadrant 2 because 2 pi over 3 is in quadrant 2. The cosine of 2 pi over 3, let's see, cosine is negative in quadrant 2, and cosine of pi over 3 is 1/2. So we get negative 1/2 plus, and we know that if one of them is 1/2, the other has to be square root of 3 over 2. In quadrant 2, sine is positive. And then we can multiply through by the 16, and we get negative 8 plus I square root of 3 times 8. And that's not really the form we like. So it's negative 8 plus 8 square root of 3 I. That wasn't too horrible. Let's see what it looks like to take negative 1 plus square root of 3i, and let's just square it. And then we're going to square the square. So we have negative 1 plus square root of 3i times negative 1 plus square root of 3i. And we remember that multiplying complex numbers in rectangular form means distributing. So we get negative 1 squared plus negative 1 times the square root of 3i minus square root of 3i plus square root of 3i. squared. And that's 1. I've got a negative square root of 3i minus another square root of 3i. So this is minus 2 square root of 3i. Square root of 3 squared is 3, and I squared is negative 1. So this is negative 3, and I'm going to move that up front. So we get negative 2 minus 2 square root of 3i for z squared. We wanted to find z to the 4th. So I'm just going to multiply z squared by itself. So negative 2 minus 2 square root of 3i. Okay, and then this time we've got negative 2 squared. Let's do the other real part. So we've got minus, well, we're going to have a plus. So we've got negative times a negative. So 2 square root of 3i squared. And this is also going to be positive. Negative 2 times negative 2 square root of 3i. And then we're going to have another of that same term. So now I've got 4. 2 squared is 4. Square root of 3 squared is 3. And I squared is negative 1. So 2 square root of 3i squared is negative 12. And then we've got plus 8 square root of 3i. And that gives us negative 8 plus 8 square root of 3i. So for lower exponents, for lower powers, it's not too hard to multiply through. But it's much more elegant to change a rectangular complex number into polar form and use de Moivre's theorem. We're not going to prove de Moivre's theorem for roots, but this is where the elegance of complex numbers in polar form really starts to shine. If we have z equals r cosine theta plus I sine theta, and n is an integer, then z to the 1 over n, and remember, z to the 1 over n is the nth root of z, is equal to the nth root of r times the cosine of theta plus 2k pi over n plus I sine theta plus 2k pi over n, where k goes from 0 up to n minus 1. A little crazy, but I bet it's going to be good. Let's see. Let's let z be 16 cosine of 5 pi over 3 plus I sine 5 pi over 3. And we want to find the fourth root. Which means we want to find z to the 1/4. So our n is equal to 4. So we need the fourth root of 16. And then, let's see, theta is 5 pi over 3 plus 2k pi all over n. N is 4. And then we have this same weird term again, 5 pi over 3 plus 2k pi all over 4. So we need to do two things before we can write down solutions. We need to make this complex fraction a regular fraction, and we need to take the fourth root of 16. Well, the fourth root of 16 is just 2. And let's see, we've got 5 pi over 3 plus 2k pi, all divided by 4. The inside denominator, the denominator of the fraction inside, is 3. So I'm going to multiply by 3 over 3. And now I'm going to distribute. So we've got 5 pi over 3 times 3 plus 2k pi times 3, all divided by 4 times 3. And 5 pi over 3 times 3, we can see that the 3's divide out. So we're left with 5 pi. 2k pi times 3 will be 6k pi. And 4 times 3 is 12. K, what is K? Wait, oh, okay. K starts at 0 and it goes up by the integers until we get to n minus 1. So for this question, K is equal to 0, 1, 2, and 3. So now we've got the fourth root of z is equal to 2 cis 5 pi plus 6k pi over 12, where k is equal to 0, 1, 2, and 3. So we've got, let's call this sub k. So we've got z to the 4th sub 0, z to the 4th sub 1, z to the 4th sub 2, and z to the 4th sub 3, where these again are the k values. So here k equals 0, k equals 1, k equals 2, k equals 3. And we're looking at k values in this situation. So we've got 2 cis 5 pi plus 6. Let's see, k is 0 pi over 12. 2 says 5 pi plus 6 times. Here k is 1, so 6 times 1 times pi over 12. Two says 5 pi. Now k is 2, so 6 times 2 pi over 12. And finally, we have k equals 3. So 2 says 5 pi plus 6 times 3 pi over 12. So let's see, 6 times 0 is 0, 5 pi over 12. Six times 1 is 6. Pi plus 5 pi is 11 pi. Six times 2 is 12, plus 5 is 17. And 6 times 3 is 18, plus 5 is 23. Just 1 second. Okay, I've got to text my partner really fast. All right. Oh yeah, go ahead and sign in. It's always nice. And let's look at a question where we start with a number in rectangular form, and we want to find the fifth root. And I thought this was a fun question because this is a point on the unit circle. This is in quadrant 2. And I know that 1/2 square root of 3 over 2 goes with pi over 3. So this must be 2 pi over 3 negative 1/2, comma, square root of 3 over 2. So we should get r equals 1. And we should get the angle is 2 pi over 3. So let's see. R is the square root of a squared plus b squared. A is negative 1/2. And b is square root of 3 over 2. Negative times negative is positive. 1/2 times 1/2 is 1/4. Square root of 3 squared is 3. 2 squared is 4. And 1/4 plus 3/4 is 4/4, which is 1. The square root of 1 is 1. Okay, great. That's what we expected. We also know that the tangent of theta will be b over a. So it will be square root of 3 over 2 divided by negative 1/2. We can multiply by 2 over 2, and we get square root of 3 over negative 1, which is just negative square root of 3. The arctan of negative square root of 3, well, that's going to be in the 4th quadrant. And since sine is square root of 3 over 2, I know that we're at pi over 3. It's negative, so I must be at negative pi over 3. To move it into the 2nd quadrant, we're going to subtract this value from pi, and we get 2 pi over 3. Yay. Now we've got our number in polar form. So z equals negative 1/2 plus square root of 3 over 2i is also equal to 1 times cosine 2 pi over 3 plus I sine 2 pi over 3. And it's loads easier to write this as 1 cis 2 pi over 3. Now I want to find the 5th roots of z. That means I need to find the 5th roots of 1. And we're going to have cis, let's see, it'll be 2 pi over 3, because that's our angle, plus 2 k pi all over n, and n is 5. We want to do 2 things. We want to take the 5th root of 1, which is just 1. Just 1 sec. I'll be right back. My most spoiled kitten got in here in my office, and she needed to get out so that she could have breakfast. Okay, so we took the 5th root of 1. We also need to simplify this complex fraction. So we've got 2 pi over 3 plus 2k pi all over 5. The inside denominator is 3. So I'm going to multiply numerator and denominator by that same number. We get 2 pi over 3 times 3 plus 2k pi times 3. So we're just distributing that. Divided by 5 times 3. And that gives us, here the 3's divide out, we're left with 2 pi plus 6 k pi over 15. And since n is equal to 5, the values for k will go from 0 up to 4, because we go up to n minus 1. So let's write the form of z to the 1/5. We said that r to the 1/5, that's the 5th root of 1. Well, 1 times 1 times 1 times 1 is 1. And then we've got cis of 2 pi plus 6k pi all over 15, where k is 0, 1, 2, 3, and 4. And now we just write them up. Let's see, let's let z to the 1/5 sub k be the general, so that we've got z naught, z1, z2, z3, and z4. And let's fill in. We've got cis 2 pi plus 6 times 0 pi over 15, 1 times cis 2 pi plus 6 times 1 times pi over 15. K is 2, so we've got 1 times cis 2 pi plus 6 times 2 times pi over 15. And then k equals 3 and k equals 4. So 2 pi plus 6 times 3 times pi over 15, and 1 times cis 2 pi plus 6 times 4 times pi over 15. Well, 6 times 0 is 0, so we get 2 pi over 15. Six times 1 is 6, plus 2 is 8. Twelve. 6 times 2 is 12, plus 2 is 14. Six times 3 is 18, plus 2 is 20. And you notice this one we can reduce. This is the only one, though, so far. Because 2 over 15, nothing is common. 8 over 15, nothing is common. 14 over 15, nothing is common. 20 over 15, 5 is common. So we'll divide that out in a second. 6 times 4 is 24, plus 2 more is 26. And let's go ahead and reduce. 5 goes into 24 times. 5 goes into 15 3 times. So this z sub 3 will be 1 cis 4 pi over 3. Now, this one, we started with a point in rectangular coordinates. So we need to write our answer in rectangular form, but we have some really bizarre angles. So this is great fun. Let's look at, we've got z naught is this 2 pi over 15. Z1 is this 8 pi over 15. Z2, 14 pi over 15. Z3 is 4 pi over 3. And Z4 is this 26 pi over 15. I say this is great fun because except for 4 pi over 3, these values for our argument are not standard. 15th of a rotation is 12 degrees. So it does go into 180 evenly. However, in order to find the cosine and the sine, we'll just go ahead and use a calculator. I think my most spoiled girl dropped mine on the floor. Okay. Okay, so we've got 2 times divided by 15 equals, and we want to find the cosine, the sine. And we need to do it in radians because because the number is in radians, duh, because we've got pi's in there. Okay, so the sine is 0.41. The cosine is 0.91. And remember that all throughout R was 1. Now we have 8 times pi divided by 15. Okay, good. Okay, wait. 8 times pi divided by 15. Oh, duh. Okay, so let's see. This is less than 2 pi, because 2 pi would be 30 pi over 15. Oh, it's in radians. Duh. Okay, times pi divided by 15 equals, we get that the sign is 0.99. And that the cosine is 0.10. Now we have 14 pi times 14 pi over 15, so 14 times pi divided by 15 equals 14 times pi divided by 15 equals, and the sign is 0.21. And the cosine is 0.98. The cosine of 4 pi over 3, let's see, 4 pi over 3 is in quadrant 4, quadrant 3. So it'll be negative 1/2. So negative 0.5 minus, and sine is square root of 3 over 2. It's negative, but 3 square root divided by 2 is approximately 0.87. Then we have 26 times pi divided by 15 equals, there we go. Sine is negative 0.74. Oh, heck, pardon my language. So we have 26 times pi divided by 15. Cosine is 0.67. And these are our 4 answers. So it's cool, to me anyway, it's cool that we can start with a number that is in rectangular form, but not anything that I can go, well, I know what the 5th root of that is. And we can find all of the 5th roots of that number. There are some try thises at the bottom of the notes, and I'm setting this up so that y'all can do, excuse me, these 4 questions, and I've got a few more that I'm adding. Let's take a 5-minute break, and we'll come back and we'll begin with My brain just stopped. Oh, we'll begin with vectors.